All right, everybody. This is a very important lecture. There is a topic that is not covered by your book that is covered by the AP Physics C exam because it involves our good old friend, the differential equation. And so we're going to analyze this thing the same way we analyze simple harmonic motion. And it's basically adding the idea of there being drag or air resistance. When we did projectile motion, we ignored air resistance, and that's a rather silly thing to do because we live at the surface of the Earth, and there is quite a bit of air resistance. So basically, what we're going to do is we're going to imagine dropping something from a high place, and we're also going to assume that there is an air resistance which is equal to minus b times v. Air resistance is somehow proportional to velocity. The faster you're going, the more air resistance you have, and the constant of proportionality is called b. It's a very common way to do this. You could use the letter c. There are other models, by the way. C times v squared has been used. This is a very good one for low speed flow before it becomes turbulent. So this is the drag force here. I'll put drag. And negative just means it's a retarding force. It's a force that holds back. It's opposite the motion is what that's saying. So let's just spitball and brainstorm what's going to happen here. So down this side here, at first, when you jump out of the airplane or whatever you're doing to get dropped from a high place, at first, the free body diagram is very simple. You simply have weight. So if we were to look at Newton's second law, we would put in your weight as the net force. You aren't moving yet, so there is no drag. And we would conclude that your acceleration would be g at first. But then you would start moving, and you would still have weight. But now there would be a small upwards force of b times v. Not very big. You've just started moving. You've been accelerating, so you've got some velocity. You're getting a little bit of drag, but not a whole lot. And now we do this again, and it turns out a little different. Now we have m times g minus b times v. That's the net force, and that equals m times a. If we divide through by m, that's a very interesting sound. Okay, I'm going to have to deal with that. One moment, please. Just like that, the sound magically stops. Interesting. I think I've got a poltergeist. Okay, dividing through by m to clean things up leads us to the fact that acceleration is going to be g minus this velocity-dependent amount. So your acceleration is going to drop by an amount that slowly increases. So your acceleration is decreasing. And then eventually, you're going to get to a situation where there's just as much upwards force as there is downwards force, and you've reached equilibrium. And this is going to happen whenever b times v is equal in magnitude to m times g, which means we're going to have a terminal velocity, which is mg over b. So I'll put a circle around this, but I'm putting a box around this. We're going to need this later. This is called terminal velocity. Doesn't mean you're going to die. Just means your velocity will not ever increase above this number, mg over b. Under this model, this is an assumption. Pretty darn good assumption, but there you go. So keep that in mind. We're going to use that later. Just to put things in perspective, let's see if we can graph what's going to happen. And again, we're not really solving this. We're just spitballing. We're analyzing the forces to see what the motion is going to be like. At first, it's high acceleration, low velocity. Then the acceleration drops while the velocity comes up, and then eventually the velocity reaches a fixed number and the acceleration stops. So let's make a graph of acceleration versus time. Well, we know that the acceleration is going to start at the value of g, and it's going to decrease to 0. But I suspect that it's going to have some curvature to it. I suspect that the acceleration is going to decrease slowly at first and then more quickly later. So I suspect we're looking at a thing that kind of goes asymptotic to 0. I suspect that's the shape we're going to get. I don't know what you want to call that. Is it decaying exponential or something like that? Now, this is the more complicated one. What's going to happen with the velocity? Well, we know that the acceleration is high, but we do know that we start at 0 velocity. And with a high acceleration means you have a high slope. So we're going to have a high slope, but then that slope is going to decrease down to 0. And we do know that we're going to peak out at this terminal velocity. So we need something that has a steep slope and then is asymptotic towards this terminal velocity. So that's about the shape I think we're going to get. Now, this is really spitballing to kind of guess at what the position versus time thing is. I guess we know that when this goes horizontal, we will have some sort of linear increase. That's right, because it isn't the slope of this graph is that graph, or we can think of it as area under the curve, and the area under the curve is increasing. It's increasing, but then it's increasing more and more quickly because we have taller and taller strips we're exposing. So I suspect that what we're going to get here is something that does this and then linear. So we have some sort of exponential rise followed by a linear regime. This is a decaying exponential. And this is like a constant minus an exponential. Because we're flipping the exponential decay over. So constant minus a decaying exponential. Put a decaying in there if I had to describe this. So those are that's just we solved a substantial amount of stuff without really doing a whole lot of math, but it's time to do the math. And I got to tell you, the math is it's a doozy. Okay, so you're gonna have to buckle up, and I'm gonna go through this thing, and you're gonna make sure I don't make any mistakes. Oh God, I hope I don't make any mistakes. Because I have made mistakes doing this. So how do you really solve this, like numerically? How do we get a freaking function, not just guessing at the graph? Okay. Well, the way you do it is what we did before. What we did before is we wrote down Newton's second law. And we put in the forces, and we generated a differential equation, and we solved that differential equation. In this case, we can look towards our what's going on in the middle of the thing to get our F net, because this is in general what F net is, right? It reverts to this when V is 0, and it reverts to this when those two are equal. So we can put in here that M times G minus B times V equals M times A. And once again, let's divide through by M, G minus B over MV equals A. And now we're going to write A as the first derivative of velocity. Last time we had a theta here and an acceleration or angular acceleration here, and we had a second derivative. This time it's a first derivative. So G minus B over M times V equals dV dt. And this is a first order linear differential equation, the solution of which is going to be our velocity as a function of time. And once we get velocity as a function of time, we can integrate or differentiate to find the other things that we need to know. So in the past, we solved these things by guess and check. And guess and check. What function, if you take a derivative of it, gives you back the same function, but with a constant out front? And then maybe this is some sort of constant of differentiation or something like that. I don't know. But basically, that's what we're looking for. And many of you could probably guess that the function of interest is some sort of e to the something, an exponential function. But I've got a way for us to be told that that's what's going on. It is a technique called separation of variables. And separation of variables just means splitting up the v's and the t's here, getting all the things having to do with velocity on the one side, all the things having to do with time on the other side, and then integrating your way out of this mess. You see, this is a differential equation. So if you could manage to integrate both sides, then you don't have a differential equation anymore. You have an algebraic equation. So we're going to run into some snags. This is going to get a little hairy before it gets over. I'm just warning you. So let's do that. Let's take all the things on this side, because they have a v in them, and let's bring them underneath this fraction, and let's take this dt and put it on the other side. So dt goes to this side. And on this side, we're going to have dv divided by g minus b over mv. I'm putting that in parentheses because that's an expression. Now, we can get out of this mess if we just integrate both sides. Integrate this side, integrate that side. Make sure that your limits of integration are consistent on both sides. So on this side, okay, here's where we run into trouble. Limits of integration. You need limits of integration so that you have a definite integral, so that you don't have to include a plus c. That was always the bane of my existence in calculus, having to add that plus c and wondering what that was for. When I took physics, I understood that the plus c was just an offset, a starting point from what your initial conditions were. So if you include the initial conditions, you don't have to deal with that. But if you're going to integrate one side with respect to t and the other side with respect to v, these need to be consistent. But I don't really know when this problem ends. So we're going to do something that I like to do called a definite indefinite integral, or an indefinite definite integral, however you want to say it. This is a phrase I coined myself. There's probably another word for it. My starting point is going to be 0 in terms of time and 0 in terms of velocity. But my ending point is going to be some arbitrary time in the middle of the problem somewhere. I'm going to call it t. And that will give me an arbitrary velocity in the middle of the problem. This velocity is not the terminal velocity. I may not let the problem go that long. I'm just going to stop at some other point in the problem. That's how I'm going to get a velocity function as a function of time. Okay, the left-hand side could not be simpler. You integrate nothing dt, or the number 1 dt, you get a t, you put in t and you minus 0, this side turns into t. Over here we have ourselves a little bit of a problem. This is a giant freaking Mesopotamia. I mean, you could think of it as a polynomial, but the polynomial has a power here. First of all, you have a to the -1 power for this expression, and then this thing, it's just, oh, it's -1 power. This is crazy. So we need a technique to get through this, and there is a technique that lets you solve these things. The technique is called a U-substitution. U-substitution means, why don't you take some complicated expression and call it U, and then figure out if you can recast this integral in terms of an integral of U instead of V. And it works in this situation. And let me walk you through it, because some people are scared by this, and I didn't particularly like it either when I first started doing it, but it's not that hard. First thing you do is guess at something that could be U. I'm going to guess that all this crap in parentheses could be U. So oh, this is not a good pen. Let U equal the quantity g minus b over m times v. Now we need to figure out a wiggle. This is a differential, a small wiggle in v, so we need to know what a wiggle in u looks like. So du, a wiggle in u, we take the derivative of this to find out what a wiggle in v looks like. Well, g doesn't have any v on it, so its derivative is 0. And so we have a minus b over m dv. So we have a constant times the wiggle in v. So a wiggle in u is a constant, a negative constant times a wiggle in v. Now, this is all fine and dandy, and a lot of people stop here, but this is not how you use it. This is not how you use it because you don't have minus b over m dv in here. You have dv. So let's do the algebra and get this constant to the other side. That says that minus b over m du can be a replacement for dv. Let's redo the integral and then we'll get going. The t comes down, left alone. Integral sign stays in place. I'm taking off the limits because I don't know what the limits are in terms of u. And then dv gets replaced with minus b over m du. And on the bottom of the fraction is just u. So going to the top of the page up here, do I have to draw a big old arrow? I do. Going to the top of the page up here, we have that t equals minus b over m integral du over u. Alrighty, folks. Now, this b over m is in the way. I should probably move it to the other side, but let's just focus right here on this, because I'm going to do 2 steps in the next move. I'm going to move this to the other side, and I'm going to take the integral of this. What is the integral of 1 over u du? Well, u to the minus 1 power, you try to raise the power by 1, you got u to the 0 power. It doesn't work. It doesn't follow the right rule for the for polynomials. But you can look it up, and you probably did learn this, that the integral of 1 over u du, or du over u, is the natural log of u. So let's move this to the other side, minus m over b now times t. And on this side, we're going to have the natural log of u. But u is something that we know, so we can put that back in, and then we can put our limits of integration back in, because if we get rid of u in favor of v, we can put our limits of integration back in. So that's the natural log, I'm sorry, that's like my signature, of g minus b over m times v, and that's going to be evaluated between 0 and v. Okay, one more line. We're just doing algebra, just doing math here. Putting in v here, we're going to have natural log of g minus b over m times v. Putting in 0 here, minus the natural log of g. Now this is a bit ugly. I mean, I can see my way clear to what's going to happen. What's going to happen is I'm eventually going to get a natural log on this side and some garbage on this side, and I'm going to get rid of the natural log by doing e to the something. But I can't do it when they're two separate natural logs. But there is a little known fact that the difference between two logarithms is equal to the logarithm of their quotient. So I should have made this one a little longer. And this actually can be simplified into 1 minus b over mgv. Okay, looking pretty darn good right there. So to get rid of this log, I'm going to do e to this side and e to this side. E to this side is now e to the minus m over b times t. I'm putting this as a fraction, then times t later. It's just to make things fit a little better. E to this side, the e cancels the natural log, and all we have is 1 minus b over mg times v. Okay, let's scramble some things around, because this right now is a function of t as a function of v. We want a function that's v as a function of t. So let's move the e to the something over here, move this thing over here. So we're going to have b over mgv on one side, and 1 minus e to the minus b over m times t on that side. Let's get rid of this. V is equal to mg over b times the quantity 1 minus e to the minus b over m times t. And this is the solution. That is the velocity as a function of time. The velocity as a function of time is some constant times 1 minus an exponential, a decaying exponential. We said that was going to be the case. I want you to notice one more thing. mg over b. This is terminal velocity. So our velocity is terminal velocity minus something at any given time. And we can see that this gives us back our curve, because look, when t is 0, this term is 1, and 1 minus 1 is 0, so the velocity will be 0. This curve starts at 0. And then as t increases, this thing shrinks away from 1 down towards 0, meaning we're heading towards vt. So vt, it does that. If you wanted to solve for the acceleration, you could do, what do? Do you take a derivative? No, you take an integral. You'd have to integrate this. And if you want to solve for the position, no, you take a derivative of this to get the acceleration, and you integrate it to get the position. But it all works out. Let me make sure I covered everything I wanted to do. I suppose, just for completeness, and because we're not quite at 20 minutes, let's go ahead and do that. Let's find the acceleration and prove that it does what we want. So here we go. We are starting with v equals vt. Actually, no, I'll write it out. V equals mg over b times 1 minus e to the minus b over m times t. There we go. And now we're going to take a derivative of that with respect to time. So we leave the mg over b alone. Taking a derivative of 1 doesn't do anything. So we have a minus sign and put the minus sign out front. And then we have the derivative of this, which is e to the same thing times whatever's in the top up here, minus b over m. And look, the minus signs cancel, the m's cancel, the b's cancel, and we wind up with g times e to the minus b over mt, which is the acceleration, which is a decaying exponential. Oh gosh, whoops, sorry guys, sorry. Got carried away. So not bad work if you can get it. We did all the same stuff that we did before. First of all, we spitballed. We kind of thought about what was going on and made some predictions so we knew where we were going. Then we got down and dirty. We wrote Newton's second law. We put in the force law. We moved some things around and we wrote the acceleration as a derivative of something that's on the other side. In this case, it was a first derivative, so I used the technique of separation of variables, moving all the t stuff to one side, v stuff to the other. We had to go through a U-substitution to make this work out, and as a result, we got a natural log. And with some algebraic manipulation, we groomed the natural log into some sort of form where we could then do e to both sides, and we got e to a constant on this side, or not constant, but a linear function on this side, and we got rid of the natural log on that side, and we unscrambled it to get velocity as a function of time, which obeyed kind of the shape we predicted. Then we took a derivative to get a decaying exponential, which again is starting at g and then having this kind of shape. Okay. Nice work, guys. Now we have one more thing we need to do, and that is to repeat this process, well, this process anyway, and with a small change, and that is that if we start on the ground and throw something up with a velocity vi, how will drag affect that? So that's our next task.